Okay, so our last speaker of the morning session is Dr. Andrew Kahng. He's a professor of CSE and ECE and holder of the Endowed Chair in High Performance Computing at UC San Diego. He's well known for his extensive work in electronic design automation broadly, and more specifically physical design automation. He's written an excellent book on the topic, which I know since I use it in one of my courses. He's been a visiting scientist at Cadence and was the founder and CTO at Blaze at DFM. He's an IEEE and ACM fellow, published over 400 journal and conference papers, lots of numerous Best Paper Awards. And so we're excited to have Andrew here to bring an EDA perspective to the workshop, and more specifically to speak about the work he's leading on OpenRoad, a new US DARPA project with the goal of revolutionizing open source EDA, and obviously going to have a very big impact on open and agile hardware design. So let's welcome Andrew.
Thank you very much for the kind introduction and the invitation to attend this just amazing workshop. So fortunately, out of my very much of a hash of a title, Chris asked me to focus on this part. And my story begins with the crises of design, cost, expertise, and unpredictability. Design cost is engineers, licenses, and schedule, and risk. And this linear trace in blue shows that wafer cost always ends up at a nickel or a dime per square millimeter in a mature process, while the curve at the right shows that the cost of designing that square millimeter is out of control. And compounding this is the non-scaling of quality, which is basically Dave Patterson's slide number 2. With every new technology node, yes, you can print twice as many transistors in a given area as before, which is available density, but you cannot fit twice as many useful transistors going node to node, which is realizable density. And this design capability gap has been highlighted, goes back well over a decade. Design is just too difficult, and thank you very much to Serge for his simplified view of the SoC design process. Helps make my point. A modern place and route tool today has more than 10,000 command option combinations for the lucky user. And for the latest nodes, tools have very complex procs embedded in them to handle complex design rules, so outcomes are harder to predict, and expert users are really needed, which brings cost and risk that nobody wants. And we still live in a computer-aided mindset as opposed to a design automation mindset. Again, this assumes expert users who may not exist. And by the way, none of us in this room or our students are expert users. Just trust me on that. So how do we escape this local minimum? One path back is automation with self-driving design tools and flows. And the DARPA IDEA program has been mentioned. It aims for hardware compilers 2.0, no humans, 24-hour turnaround time, eventually with zero loss of quality. So, Mark, thank you for not scoffing too loudly. The traditional EDA focus has been on tools that eke out that last picosecond of clock period. But we're shifting that focus to tools that don't require any expertise or time to tape out a working chip. So no humans 24-hour design capability potentially brings this huge chunk of what the ITRS always called design-based equivalent scaling, because Moore's law equivalences 1% to 1 week. And the broader impact, of course, is to restore accessibility of silicon to designers. OpenRoad, which Chris mentioned, is one project in the IDEA program. It aims directly at this no humans 24-hour digital design flow while also catalyzing an open source ecosystem for tool developers. The team has 5 universities plus Qualcomm and ARM. And to get from here to there, lower to upper, we pursue 3 research, I would say, foundational technologies. Extreme partitioning, because you have to decompose the design problem into bite-sized chunks in 24 hours. Orchestration of distributed and parallel optimization threads. And machine learning to model and predict what will happen when a heuristic optimization is launched in a certain way on a certain design input with a certain target. And there's also freedoms from choice, just as self-driving cars will eventually have no steering wheels or gas pedals. So machine learning is quite central here. How to partition, how to orchestrate, how to identify and kill a doomed thread, etc. And there are also some driving mindsets. The user must see predictability because it's no humans. Whatever goes on under the hood. Partitioning and restrictions win time, but obviously lose quality. So we have to win quality back with machine learning and parallel search in the cloud. And it's worth pointing out that when any scaling trajectory stops in any technology, the very last levers are always going to be quality, schedule, and cost. This is the transition from basically innovation to optimization that always occurs. And I believe that there's more than a node of scaling on the table here. The OpenRoad project's initial target is the digital RTL to GDS flow, logic synthesis through routing and then layout finishing. In terms of delivery, open source code and no human in the loop are mandatory. The inputs shown up at the top are all industry standard formats, Verilog, constraints, timing power libraries, and so on. The flow also requires additional config files and characterizations for reasons that you can find on our website. The output is final routing plus timing and power reports, and today we are about a year before the V1 release. And some more information is at these links. I post all slides on the website of my group, including talk notes. So, why open source? Why is this required? So a non-trivial part of my job these days is actually going around explaining why everyone, including commercial EDA and foundries, wins if open source EDA becomes a reality, at least in the research and hobbyist community. Just from the EDA research perspective, let me just say a few words. Open source will be a huge boost if it materializes. We would get clarity and transparency while today's commercial licenses explicitly forbid benchmarking. We would get better science. Every result is reproducible, whereas today our research is irreproducible by construction. Namely, we cannot publish or even share the scripts that contain copyrighted tickle commands that we use to drive commercial tools in our experiments. So think about that. And we would avoid reinventing wheels, trying to reconstruct 3,000 lines of C code from 15 lines of pseudocode that are 2 inches of a 6-page paper. It's just stupid. And writing yet another block placer or buffer inserter or placement legalizer, we can spend our students' time and brain power in better ways. And if you want more people working on next generation tools, please help, as I hope to mention below. It's kind of well known that a viable open source ecosystem requires critical mass and critical quality and attention. So just to buy into the game. So especially in open source EDA, which has been tried before and which has failed before, outreach and culture change are crucial. And so we have a number of outreach efforts like workshops, contests, awards, and so on. And as I just alluded to, open source EDA is not new. It was mentioned earlier that the industry itself has its roots in Berkeley and MIT open sourcing. 20 years ago, a bookshelf of open source tools was launched by the Marco Design and Test Focus Center, the first one. IEEE's Council on EDA sponsors an academic reference tool flow that is mostly open. It's kind of a parallel universe to commercial EDA. And if you follow the links in the slides, there's a wiki that collects some census data on open source EDA. All the links are in this wiki. There's raw data. There's a recent uptick that you can see coincident with ERI and IDEA, but as you can imagine, it's fragmented, lots of forking, chaotic, and so on. If you dig into the demographics of the data, you can see, for example, that most open source tools are in the digital space. That's the blue 81% of the pie chart. Or you can readily discern that there's almost no verification and test that's open source today. Now, 18 days ago at the Design Automation Conference, Tom Spyru of Intel showed this slide about the EDA industry's 40-year learning curve on how to architect RTL to GDS. That's synthesis, place, and route. Point tools connected by files was the 1980s, which broke, and then we had to connect synthesis and layout to timing, think Magma. And then miscorrelations and runtimes forced really, really tight coupling of engines onto a shared incremental substrate. And the most recent decade has been about multi-threading and sort of hyper-optimization of what we had in the 2000s. So all of commercial EDA today has this architecture shown here with a shared physical data model and a shared netlist, i.e. timing graph, as a substrate. And so if synthesis decides to upsize a gate, this is hopeless, it changes the netlist, and there are callbacks to the timer or incremental place and route, and then the place and route changes will imply parasitic changes, which are used by the delay calculator if the timer asks for an updated delay or a slew, and so on. And today, this architecture supports many thousands of changes in the netlist per second. So you cannot do this with files running around back and forth between tools, which unfortunately is where we are in academia and in OpenRoad today. Our alpha is a 1980s file-based flow, which means that the v1.0 production release target implies moving 20 years up on this learning curve in the next 12 months to a shared incremental architecture, which would be the first ever to be permissive open source. So if you watch this effort, first comes a tool chain, hopefully very soon, that delivers manufacturable DRC clean layout in a Foundry node, and then tight integration. Okay, so now we're into bonus content because I've delivered on Chris's mandate or instructions. And so until Chris removes me from this podium, we will continue. So in the spirit of now it's only food for thought for ISCA folks, let me say a bit about these words in the title. One observation coming here is that we kind of live in different worlds, right? The IC design world spends $500 million to get to high volume on a flagship application processor chip, and just look at who sponsors my research. Driving commercial EDA tools is difficult. It's hard to predict value that will eventually be extracted from future technology. It's hard to predict in advance. And of course, this world includes Intel, NVIDIA, and a number of others who are in this room today. As for the EDA suppliers today, 0.5% of clock power reduction is a home run. Whereas, at least in some parts of the architecture world, you've got these big levers, and improvement numbers in papers can be 40%, 25x. And when I collaborate with architects, my papers say this too, like 50% performance improvement ISO cost. And so the food for thought is, how is this possible? Why are our two worlds so different? So I've pestered a lot of folks over the years about best practice, golden methodologies for power and temperature, or reliability assessments, because you have to measure before you can improve or optimize. And as you can see, this picture here spans from Parsec and Splash2 and Gem5, Sniper, Hotspot, through NC Verilog, down to Innovus and Red Hawk and more. And I guess Jason's question to Vivian highlighted this. How do you estimate power? It would be nice to have a tool, was the answer, as I recall. Okay. So how does one measure power or MTTF with all of these difficult chicken and egg loops, right? STAIR, STA thermal, static timing analysis, reliability, workload and thermal, across time and spatial scales, and across layers of system hierarchy. So architecture is up here in the right. Design and EDA kind of struggle to understand anything down there in the lower left, and process is somewhere outside of this picture, sort of to the left and bottom. So, well, coming here, I looked at the program and, architects are really rock stars. And I really mean it about this title. I feel like I'm a fan. And architects get these 25x results in their papers. Whereas, and I say this with admiration only, Richard Newton, in a keynote to my field in the early 1990s, told us that place and route was a solved problem. So look at what I work on 25 years later. I would have to say our DNA is different. What I want to say here is that whenever I've come close to touching the architecture universe with Orion 2 and 3 or Cacti 7 or work on the ITRS roadmap, I find myself always asking whether there can be better calibrations, better estimators, better oracles for architectural design space exploration, because ultimately things have to boil down to the accuracy and quality of objective function estimations or evaluations, which are baked into your optimizations, whose outcomes determine product value in markets. And so a key missing piece here is what space of tape-out databases was possible when you did that estimation or front-end assessment. And that's maybe a connection to what I'm working on. Here's one opportunity to bring architects closer. It takes years to develop a CAD tool, years to develop an SoC architecture, years to bring up a technology node. And to align these developments better, we seek visibility into the key IPs like NAND gates or SRAM bit cells. And we also ask, what will the key system components, DSP, IOs, neural processor core, what will they look like? And my life in design for manufacturability, DFM, has evolved into a life in what we call DTCO, design technology co-optimization, which is still, in my view, a future technology. Now, I work with foundry and design technologists. Can architects join this conversation? And DTCO must evolve further into what I call true system and technology pathfinding. There are just too many possible futures. Integration, is it chiplets on interposers or monolithic 3D, CNT FETs or TFETs, ReRAM or PCRAM, buried power or backside power, approximate or stochastic, you know the litany, and every combination from this menu is somebody's paper, no doubt. As we prepare IPs and technologies, are we preparing for a next wave of deep learning or VR? You probably know, I don't. And this loop does not exist today, but if it did, I would call this picture true and complete system pathfinding. Will bringing architecture closer and marshaling the efforts of both communities help? Because there's a lot of work to do here. And right now, TCAD models and ring oscillators, I don't think they're enough for the equipment companies or foundries and fabless to determine their right bets to make. Here's a $1 billion bet which nanosheet widths should the foundry offer at the 3 nanometer node. And this is a slide on pathfinding as I gave it to Samsung Foundry a few weeks ago. So there's a large bridge to be made here. Okay. So I'm actually on time, Chris. In actually only 2 more minutes, here's the remaining words of my title and, well, some final thoughts. So what might EDA folks and architecture folks together enable? It was late last night, didn't come up with too much, but 2 obvious ideas or thoughts, food for thought, would be those machine learning powered self-driving EDA tools and flows. They will actually never exist without collaborative generation of data. And 3 keys are needed to unlock this, namely designs, tools, and technology models, which means that architects and designers and EDA technologists must work together to enable this bullet point. And what about that 40% number? Well, I would love to give architects better oracles and constructive proofs of what is achievable PPAC at the very limits of a given technology and enablement. So a more rigorously established 40%, or maybe a 50% that is discovered while your student relaxes at the beach might be possible. So we need tools and orchestrations of tools that in aggregate are smarter than the best human Innovus user today. And hopefully this is a side effect of research towards self-driving tools and flows. And recall Serge's VC bar chart and, the effect of lower cost of developing silicon. And I'm sure there's more compelling targets. So in summary, open source design technology plus bringing architecture closer plus what together might enable equals food for thought. And thank you for your attention.
So Andrew, to me, the success of EDA tools has always been laid in the answer to the following question. Will Qualcomm or Broadcom use this tool to design their mainstream next generation SoC?
So
So the question to you is, do you envision the open source backend that you're developing ever being used in that kind of high intensity, high risk commercial context?
yeah.
If so, why do you believe that?
Oh, I don't believe that. I believe, so you can find many talks where I've said explicitly what will never be designed using open source EDA and includes next generation Snapdragon is explicitly called out in those slides. So I thought you were going a different direction. So does that answer your question? Then I'll stop. But I know the naysayer arguments, and there are numerous and well taken. This is not easy, but I think this serves a certain demographic of people who want to go from their garage to silicon without actually hitting the ultimate PPAC. Yes, Luca.
Very good question. So based on the answer you just gave, if that's not going to be accomplished, do you think that the open source flow will accomplish any change in the attitude from the EDA companies that you mentioned very explicitly?
Oh, the question was about will there be change in the approach of EDA companies with respect to, let's say, proprietary scripts? You can add the metrics of the design and the design flow. That goes back to another 20-year-old project, which you can find on the web. So Metrics 2.0 is a big part of enabling machine learning in and around the IC design process. Will it induce behavior change? Well, I've certainly proposed doing the right thing to all EDA folks in commercial EDA, but they have their own business reasons for not opening up, let's say, TICL command languages or other proprietary things, benchmarking as well. But the good news is that if this ecosystem came to exist, there would be no need to require or to even want this open sourcing from the EDA industry. They can continue to exist, and they can draw IP or innovations from academia more freely and more directly.
Which is cool. I just wonder if you have any speculation on what you, if assuming success of the project, what could how could it impact the EDA?
Oh, I think it's good for the EDA industry because I have other slides which show all the gray hairs at the Design Automation Conference, right? I mean, when we make life so difficult, irreproducible research, reinventing the wheel, as I mentioned, so difficult for PhD students, why would anyone want to come to work on EDA? And this is actually what has happened. So I think it's crucial for the industry to support this, and at a debate panel at DAC, in fact, leaders from both Cadence and Synopsys were highly supportive of this, and they recognized how this can boost the efficiency of academic progress. Yes, at the back.
So a quick question, a slightly long question. A quick question is there going to be a parallel validation with commercial EDA tools? I'd love to trust these tools and be sure that or benchmark or make this benchmark.
Yeah, our team has an inbuilt user or internal design advisors group from Michigan, the usual suspects of SoC producers from Michigan, and their role is to actually provide these calibrations. ARM and Qualcomm also provide calibrations, so.
And one last thing is, you mentioned a little bit about high-level models, but you didn't go into detail about if you were looking to develop those, because you're talking about Kahng and Orion.
Oh.
But it didn't look like on your path you were thinking about
No.
developing
No. No.
Is there a place in working, so for example, this middle ground, right? You're saying, let's work with architects, which is a great thing, right? I'd love to work more with the EDA side and automate all this. But there's a reason why we have tools like Orion and Methodologies.
Right.
EDA tools are difficult, and even if we are able to automate this, we still need the whole design in order to use these tools. We still
Right.
need a complete design, which when we're doing our architecture
I know.
exploration, we don't have all the pieces. We don't want to develop all the pieces.
I know.
What
So.
I'm wondering is, have you guys thought a little bit about the middle ground and what we can do there?
Yes, and some of it is, well, a black box of 10 million lines of a detailed router with all these procs inside it obviously is not very well modeled. I have slides showing chaotic nature of commercial tool flows, which everyone understands, because you've pushed heuristics on top of heuristics on top of heuristics to the very breaking point. Chaos is natural. So another research direction is, inherently more modelable and predictable tools and flows. And, yeah, we have thought about how to, generate the bridges in the middle of this picture. And obviously they have to be done, but, journey of 1,000 miles, et cetera, right? So.
Okay, let's go ahead and take meetings.
Okay.